Hello, my name is Shiraz Farouk, and I'll be introducing my group members. First of all is Bassam, and second of all we have Tan, and thirdly we have Xavier. I'll be explaining about the tic-tac-toe game problem that we have chosen, and I'll be showing you about our data set, how I process the data set into a useful game, and the search methods. I'll start off with the background and problem statement. Firstly, you might have this question of why games. Games give us explicit rules, perfect information, and clear winning conditions, so they're ideal for testing search methods. We chose tic-tac-toe because of its finite state space. It makes it manageable for rigorous comparison. The specific challenge is simple to state but valuable. Creating an agent that makes optimal decisions and never loses, and compare it against a baseline approach. Finally, that the project goal is to measure the trade-off between intelligence, that is how optimal a policy is, and computational cost, expressed as processing or decision time. In other words, can we get perfect play without excessive runtime? Our dataset was custom generating using our Allergo Common Lisp that we learned in our labs, and contains 100 labeled board states, which are data points. Each record stores the 9-cell board, whose next player it is, and the index of the best move. Boards are represented as a list of line 9 symbols, X, O, or an empty cell, as I've shown in this table. Labels were produced by a Minimax evaluator, so each entry points to the optimal move for the state. Crucially, we only kept valid non-terminal configurations, that is, game states that would actually occur and that aren't already a win or draw, to train decision tree models reliably. The processing had three core steps. One, a valid state check. We ensured the difference between X and O counts is at most one, and no player had already won. The number two is turn consistency. We detect whose turn it is automatically. For example, if X has more marks, it is O's turn, to avoid impossible states. The third one is minimax labeling. A recursive minimax function examines every legal move and assigns a best move label using a simple scoring scheme. Plus 10 for win, minus 10 for loss. These steps guarantee clean, correct labeled inputs for downstream learning. Thank you very much.
Hi, I'm Xavier, and right now I'm going to talk about decision tree model and hyperparameters. First, the classification approach. We transform the problem from a search-based task into a supervised classification problem. Each board state is treated as input, and the output is the optimal move. This allows the system to make decision instantly, without running Minimax during the gameplay. Next is the learning process. The decision tree learns a direct mapping from board features to optimal moves using labeled data generated by Minimax. Once trained, the tree can predict good moves efficiently at runtime. For the splitting criteria, we use entropy and information gain. This matrix helps the tree choose the features that best separate the data, reducing uncertainty at each decision node. Finally, the hyperparameter setting. We set a minimum number of samples per node to prevent overlifting. This avoids the model learning noisy or overly specific patterns, keeping the decision tree stable and general. The next is informed search or Minimax algorithm. Minimax performs a depth-first search across the entire game tree to evaluate all possible future outcomes. The goal is to always select the move that guarantees the best results for the AI. For scoring, A win is plus 10, a loss is minus 10, and a draw is 0, which depth base adjustment to prefer faster wins. In the decision process, the AI acts as the maximizer, choosing the highest score, while the human player is assumed to play optimally as the minimizer. Also introduce a fast start heuristic. When the board is empty, the AI instantly chooses the center position instead of running minimax. This removes the initial daily and improves performance without affecting optimality. Overall, minimax guarantees optimal play and zero losses, but the cost of higher computation, especially early in the game.
This slide, I will explain our baseline agent, which is the uninformed search, also called the random bot. The main idea here is simple. This agent does not think ahead at all. Instead, it first lists all legal moves available on the board, and then it chooses one move randomly with equal probability. Because of this, the algorithm is extremely efficient. It runs in constant time, meaning it does not depend on the game state complexity. As a result, the execution time is practically instant. However, this speed comes with a major drawback. Since the bot has no look ahead, it does not evaluate future consequences. It cannot predict whether a move will lead to a win, loss, or draw. This causes strategic failure. For example, the bot may fail to block an opponent's immediate winning move or miss an obvious opportunity to win. So overall, this random bot is fast but unintelligent, and we mainly use it as comparison baseline to highlight how much strategic reasoning actually matters. Moving on to the evaluation and analysis. Here, we compare the informed search agent using Minimax with the uninformed random agent. Starting with the Minimax agent, during the opening phase, it explored 63,904 nodes, which took about 7.57 seconds. This is computationally expensive, but the payoff is that the agent achieved perfect optimality, meaning a 0% loss rate. It will never lose when playing optimally. In contrast, the random agent executed instantly due to its time complexity, but it frequently failed in real gameplay situations. It often missed critical blocks and made poor decisions, leading to avoidable losses. The table below summarizes this trade-off clearly. Minimax uses exhaustive tree search, requires high memory and time, but guarantees optimal play. The random bot used stochastic selection requires almost no memory, but has no strategic awareness. So the key takeaway from this evaluation is that there is a clear trade-off between intelligence and computational cost. Higher intelligence leads to better decisions but slower performance, while faster algorithms sacrifice decision quality. This comparison strongly supports why informed search techniques like Minimax are essential for decision-making tasks, even in simple games like tic-tac-toe. And that's it for my part.
Yeah, talking about our programming code for the AI algorithms for the AI project. Firstly, we're gonna upload our coding programming file. As you can see here, the code was uploaded. Let's say we're gonna write play. Yeah, as you can see, when we wrote play, it shows two options, which is the output. The first options you can see play against the intelligent agent, which is the informed search, the Minimax algorithm. The second one is stochastic search, which or a random search algorithm. Let's say we're gonna write one, which is against the intelligent one. It's asking you to play firstly. We're gonna choose number 4. As you can see here, the AI is thinking. You're gonna take some time to check the notes to that and see what you can play. As you can see here, the analytics, the node was checked 55,504. The timing was 7 seconds, about 7 seconds. He checked like more than 50,000, sorry. As you can see here, he played in number 0 using, oh, okay. I will play. Let's say I'm gonna try to win as well. As you can see here, he blocked mine. I cannot win, and he is about to win if I didn't block his. I will block him using number 3. As you can see here, I will try to win as well using number 1. He blocked mine, and this is number 8 finally. As you can see here, you cannot win over the intelligent one, the Minimax algorithm, which is more intelligent than anyone. You just can draw with him, or he never lose. As you can see here, in the checking node, firstly was more than 50,000, then it was about 900, uh, then it become 50, then 4 the nodes, and as you can see here the time as well, he took 7 seconds in the first, then it took less than 1 second, then 0 second without thinking. That's the Minimax algorithm. Let's say we're gonna try the other one, which is the the search algorithm, the random search algorithm. Let's say number 2, which is the bot one. We're gonna choose number 1. As you can see here, the bot played without any thinking, without any checking nodes, without any taking time. He just played directly. As you can see here, I'll try to win to see what he can do with me. Choose number 4. He blocked me in the first one. Okay, I'll try to win in the other one. Yes, as you can see here, I have two choices to win. Like Israel C8 and I win. And if you want to end the game before you win or drawing, you just can write end and end the game. In conclusion, in this project, we built a text-based tic-tac-toe system with two agents, a smart Minimax agent and a random bot. We found that while the Minimax agent always wins, it needs more processing power. We improved the opening move with a fast start optimization. Next, we plan to add alpha beta pairing for faster searching, handle larger boards, and create a graphical interface for easier use. That's all, and thank you so much.